Okay, sorry part 2 got so long. I think part 3 will be better, but we'll find out. All right, so looking here, there we go. Okay, State of Michigan says that if more than 7% of households in a city exceed the safe limit for lead, the city needs to switch to bottled water. A concerned citizen takes a random sample of 100 households and finds that 12 have unsafe water. Do the data provide convincing evidence that Rockford should switch to bottled water? There was like a whole like context here that I thought this is a made up situation, unlike the Flint, Michigan thing, but I didn't totally edit it out. So, you know, that Michigan, I don't know. Also, you can probably tell a lot of my lessons come from some stats teachers in Michigan because like every problem's about Michigan. Okay, it's fine. Here we go. All right, so first of all, we need to figure out what our hypotheses would be if we were going to perform a significance test. I want you to try this problem, and then also questions 2, 3, and 4. Further if you can, but hopefully you can get through about 1 through 4, and then when you're ready, hit play and we can go over those together. All right, question 1. So our hypotheses here, first of all, I just like to sometimes just even figure out what they are. Our null hypothesis would be that the water is safe. Our alternative hypothesis would be that our water is unsafe. You don't have to write this part out, but sometimes if you get stuck on like articulating what the hypotheses are, sometimes it's helpful to like take a step back and think about them in terms of the problem. Okay, so if the water is safe, that would mean that our our proportion is equal to 0.07. If the water is unsafe, that means that P is greater than 0.07. And we always have to define what P is referring to. Here it is the true proportion of all households with unsafe water. All right, next question. After conducting a significance test, and that's that whole state plan do conclude process, a p-value is found of 0.025. Interpret the value. So what this would mean is that assuming our null hypothesis is true, and I'm just going to state what that is, that p is equal to 0.07, there is a 0.025 probability of getting a p-hat of 0.12 or greater just by chance. Okay, the next part is asking us if we should reject our null hypothesis or fail to reject. And because our p-value, 0.025, is so small, it's less than 0.05, we reject the null hypothesis. Michigan should switch to bottled water. So just what this means, the chance of getting 12 out of 100 with unsafe levels, if truly only 7% had unsafe levels, the chance of getting 12 tested results of unsafe is so rare, 0.025, we can conclude that the null hypothesis is not true, that the proportion is something that's going to be bigger than 0.07. All right, next question is a key question for the day. Let's suppose this decision is wrong, this decision about switching to bottled water. What would be a consequence of this? So this we can kind of think about. So like if a whole state or whatever decides to switch to bottled water unnecessarily, what would be a problem with that? We could talk about money. that the state would be spending a lot more money on bottled water when they didn't need to. We could talk about environmental impact of bottled water. I can spell things. There's probably other things you guys can think about too. I feel like whenever I ask a question like this, you guys can always come up with like 10 things I never thought of. But biggest one here, I think, is money, environment. To me, there's probably other stuff too. Yeah, so this is a specific type of error that we're going to come back to in a little bit. So that's why I put a star by it. All right, for question 5. If the water is actually safe, what is the probability that this error will occur? And I'm just going to tell you that this type of error is always just equal to your alpha level. So it's going to be 5%. We'll put that in our notes in a little bit. All right, for question, I want you to try questions 6 and 7 and 8. And then when you're ready to go over those, hit play. Okay, so now let's say we did this, but our p-value was very different. It was 0.217. Should we reject the null hypothesis or do we fail to reject it? So let's see. In this case, because 0.217 is greater than 0.05, we would fail to reject the null hypothesis. And what that means is that we would keep using tap water. All right. And let's suppose this decision was wrong. Let's say we keep using tap water, but we actually shouldn't be. So for question 7, a consequence for this is that people are drinking unsafe water. And that could lead to illness or death. That's kind of the only consequences I can think of for this. Like if people are drinking tap water when they shouldn't be, main issue I think would just be illness and suffering. Maybe there's other stuff you guys can think about too. All right, and then the last question. Are the consequences in, and my numbering is off on your doc. It's great when I can catch my mistakes before I actually publish it. The consequences in questions 4 or 7 more serious. So this is sort of an ethics question. Is it worse to spend money on bottled water and also be a worse for the environment? Is that worse? Or is it more serious to have lots of people drinking unsafe water? I would probably say that the number 7 is more serious. You could maybe argue the other way, I don't know, but that's what I would see as more serious. We have to, part of the job of the government is to make sure people can like drink water and stuff. As we saw with our lesson in Flint, Michigan, sometimes it doesn't happen. But that's what I would say, due to potential loss of life. I'll say illness and loss of life. Okay. Great. So that's actually it for that activity. We're going to do some notes and then a check for understanding. So hopefully we'll clock in at under 35 minutes. Again, sorry that last one was super long. Okay. So there are 2 types of errors that we can have when we're conducting these tests. We can have a type 1 and we can also have type 2 errors. There's a handy chart that will help tell you which is which. Okay. And I honestly get these mixed up all the time. So I have this written out on a Post-it note so I don't forget which one is which. This is going to be based off of our conclusion that we got to and the actual truth. Okay, so if your null hypothesis is true or your alternative hypothesis is true, that'll help us figure out what kind of error we have. And then our conclusion, either we rejected our null hypothesis or we failed to reject it. Okay, and based off of these different things, let's switch to orange for fun. This box would be a type 1 error. If our null hypothesis is true, but we rejected it. This would be a type 2 error, and that would be our alternative hypothesis is true, but we stayed with our null hypothesis. The other boxes are not errors. Those are good. This first one up here is like we rejected our null hypothesis and our alternative is true. So like that's cool. Or down here, if we fail to reject it and it's true, that's good. Okay, so just a few notes on these different types of errors. So a type 1 error, that's again where our null hypothesis is true, but we rejected it. A type 2 is that your alternative hypothesis is true, but we failed to reject the null hypothesis. Last thing in our notes for today is that the probability of a type 1 error is equal to your significance level. Cool, so that's it for notes. Take a look at the check for understanding, and when you're ready to go over answers, hit play, and then we can go over all that stuff together. Okay, so Emilio purchased a trick coin that's supposed to land heads up 75% of the time. One of his friends wanted to test the claim. The friend flips the coin 50 times and finds that the coin lands heads up 35 times. The friend then performs a test of the following hypotheses, and here we have a different significance level. Then it's not 5%, it's 10%. Okay, so our hypotheses here, just to explain them, the null hypothesis is that the coin works as advertised. And then the alternative is that the coin does not work as advertised. All right, so first thing is just to go through what the two types of errors would be here. For a type 1 error, and look back at your notes, that is where the null hypothesis is true, but we rejected it. So what that would mean here is that the coin does work as advertised. And I'm going to say what that means, that P is equal to 0.75. But the friend finds convincing evidence that the coin is not working. And I'm going to state what that would look like. That would be that P is less than 0.75. A type 2 error here, it would be that the coin does not work as advertised. But the friend does not find evidence that it's not working. All right, so next part here, which type of error might result in Emilio returning the coin and writing a negative review? So that would be, just catching my typos here, that would be a type 1 error. That would be if Emilio returns the coin, even though it actually does work. Okay, and then last part here, for question 3, if the student were to use a 0.05 significance level instead of 0.1, would this make it more or less likely to reject the null hypothesis? When the null hypothesis is true. So again, rejecting H sub 0 or null hypothesis when it's actually true is a type 1 error. And I told you that the probability of a type 1 is equal to your significance level. So if you're reducing your significance level, that means you're going to reduce risk of a type 1 error. And that's it for part 3.